slide, please. Yeah, all right. So let's go ahead and get started. So Natasha Macbean, she is from Indiana University in Bloomington. She will be giving us a talk on evaluating terrestrial biosphere model ET and ET partitioning in the southwestern US in semi-arid ecosystems and interactions with vegetation and carbon cycling. Take it away, Natasha.
Hi, thank you very much for inviting me to speak today. I'll just share my screen and then I'll get started. Here we go. Yeah, thank you very much for inviting me. This work on evaluating particularly the Orchidea terrestrial biosphere model, evapotranspiration and ET partitioning is very much ongoing work. We've published some of it and it's still ongoing. So it was a really great opportunity to come and present this to you now, and hopefully you'll have some thoughts on some of the sort of things that we're still trying to puzzle through in terms of testing and optimizing the model. So just to dive right in, a motivation for this work, for me at least, came more from the carbon cycle. And I won't go through all the sort of history of how I got interested in semi-arid ecosystem carbon cycling, but one thing was these high-profile papers that came out in 2014-15, suggesting that semi-arid ecosystems were playing a dominant role in the global carbon cycle, interannual variability, and also the longer-term trend. And particularly Anders Ahlström's paper down at the bottom here, and shown in this figure on the right here, was really using a whole suite of these terrestrial biosphere models. And these are the types of models that form the land component of Earth system models used in IPCC climate change projections. And he was using these to show these patterns and the role of semi-arid ecosystems in global carbon cycle interannual variability. But what I won't show is some of my past work that was trying to optimize the parameters of some of these models. That's the fixed values of the models. That might be something like maximum leaf area index, all sorts of carbon cycle, vegetation dynamics related parameters. And I found that in semi-arid ecosystems, the models just weren't capturing the observations very well in terms of the vegetation seasonal cycle and long-term trends, even after we tried to optimize the parameters. And so I was wondering whether, how well the models were really doing in semi-arid ecosystems. They hadn't really been a focus of the sort of global carbon cycle modeling community, at least. These papers raised their profile very much, which was exciting, but I was keen to test these models, like the carbon and water fluxes in these ecosystems. And so then I did get an opportunity to move to the University of Arizona to do a postdoc. And I collaborated with a bunch of folks there, particularly Dave Moore, Russ Scott, and Joel Biederman, Marcy Litvak, Tom Kolb, who were gathering sites across the Southwest US semi-arid ecosystems for doing a carbon and water flux synthesis, shown by these sites here. These sites really span a range of ecosystems, from the kind of high elevation forested sites that overall are a mean sink of carbon, going through a bunch of lower elevation savanna, shrub and grassland dominated sites that really pivot between a source and a sink of carbon year to year. And Joel's synthesis paper in Global Change Biology in 2017 really showed that plant water availability, and they used evapotranspiration as a proxy for plant water availability, was really the driver of these carbon cycle dynamics, as we might expect, given we know sort of semi-arid ecosystems are very much driven by moisture availability. So this was a fantastic opportunity for me to test the Orchidea terrestrial biosphere model. I was amiss in terms of putting in a schematic here of what is included in these models, but suffice to say they do incorporate carbon cycling, energy surface balance equations, hydrology schemes. And so in theory, they should be capturing carbon and water cycling pretty well in all ecosystems, but including semi-arid ecosystems. And so initially what I did, as I mentioned, was focused on looking at carbon cycle interannual variability, particularly the net CO2 exchange, or NEE interannual variability. And so I did run the model at the sites using site level forcing, site level vegetation characteristics, and soil texture, etc. And this is sort of roughly the outcome that we got. So we have a scatter plot here of the annual NEE on the y-axis and the observed NEE on the x-axis across all these different range of sites. And we can see that the model variability is much lower than we might expect in the model. It's not capturing that mean sink or source of carbon, and those slope values should be, roughly close to 1 if we're hoping to capture interannual variability. I also looked across all the same models that were used in that Anders Ahlstrom's paper that were included in the trendy analysis. You don't need to dig into the weeds of this figure here, but just to show that most of these models are the same. They do not capture that interannual variability in the net CO2 flux. I promise you I'm going to get to ET in just a second. But suffice to say that digging into the weeds a little here, what we found was that the issue is mostly that it's the vegetation and gross carbon uptake, that it's not responding enough to changes in water availability in key growing seasons. But that, of course, begs the question of whether the models can capture the water fluxes and the water stores right in these ecosystems, because maybe the vegetation isn't responding because there's not enough water availability or variability in that water availability. So that then pushed me into testing the water stores and fluxes across a range of these southwestern US semi-arid sites, looking at both soil moisture and evapotranspiration. This was published in Hess in 2020. And so just to show you some key results here for both the Flagstaff unmanaged forest site, high elevation pine forest site, and then the Santa Rita grassland site on the right-hand side here. And the top panel is evapotranspiration, and on the bottom is normalized soil water content. And the observations are shown in black curves here. This is a daily time series just for 1 year to highlight the main results. And then we tested 2 versions of the model. One was just a 2-layer simple bucket hydrology model that used to be in many of these terrestrial biosphere models and was in most of the models, for example, in the last CMIP5 IPCC AR5 report. So that's shown in the green curves here. But most of the models now have a mechanistic description of soil moisture diffusion, vertical soil moisture diffusion in unsaturated soils based on the Richards equations. That's implemented in most of the models now. In Orchidae, we have that discretized into 11 layers. So that's shown in the blue curve in these time series here. And what we found was that, the simple 2-layer bucket model, in the upper layer, the soil moisture here just had such sort of random fluctuations that it then resulted in a fairly random fluctuations in the evapotranspiration. Whereas when we then implemented the 11-layer hydrology scheme, you can see that it's doing much better in terms of capturing those temporal dynamics. Things to point out here are, the peak fluxes that we expect to see, especially in the low elevation semi-arid regions. These are very pulse-driven ecosystems, are much better captured with that more mechanistic hydrology scheme. There's a few things that are still, still worth looking into, such as the model here dries down too quickly in response after a rainfall pulse. So that is something to keep in mind as to why that might be happening. And also we found at the higher elevation sites that we had this curious case where we overestimated soil moisture towards the end of the year or the start of the winter season. And then in the spring, underestimated the soil moisture. And we believe, in the spring, the evapotranspiration tended to be overestimated. And we believe that this might be that the snow is forming in the model in the winter, but then melting too fast. So we have an overestimate of soil moisture earlier in the winter. And then towards the spring, when we can see that there's snow on the ground in reality, actually there's bare ground and there's too much bare soil evaporation happening, which is causing an underestimate of the soil moisture and an overestimate of the ET, but that's still a kind of theory that we want to test, looking at more the snow dynamics, which then very much feeds into, snow melt very much feeds into the sort of coupled carbon, vegetation, water dynamics at these higher elevation sites in the spring. So yeah, the mechanistic soil hydrology scheme that I mentioned is in most of these models now, is doing much better at capturing these water stores and fluxes, the temporal dynamics. That's great news. And just a plug for my colleague, Nina Raoult. This is not a study I was involved in, but she is working also in the Orchidea land surface modeling group. She's used parameter optimization, particularly of a dry down rate parameter to improve very much this modeling of dry down rates. So that is something that has been able to be dealt with in the model via that work. Just a plug for that there. So yeah, looking at the mean seasonal cycles of evapotranspiration, separating out the high elevation sites from the low elevation sites, we can see again the temporal dynamics are really captured pretty well by this mechanistic 11-layer hydrology scheme, slight overestimation in the spring at the higher elevation sites, but capturing that sort of drier period at the lower elevation sites right before the monsoon rain starts, and we get an increase in mean seasonal cycle. So mostly the answer is that the models are capturing the water stores and fluxes well, with a slight caveat, and that is that in this paper we also looked at the ET partitioning. So this TET ratio, sort of data-driven estimates provided by Russ Scott at the higher elevation sites. This is based on Joe et al. 2016. And at the lower elevation sites, we have two estimates, one also from Russ Scott's paper in 2017 that is maybe a little bit more adapted for these lower elevation semi-arid sites. And so we can see that there's a couple of things that are maybe, slightly not as good as the full ET picture here. The model is in blue, that 11-layer hydrology model is in blue here, and we tend to underestimate that TET partitioning or ratio, sorry, at the higher elevation sites. And at the lower elevation sites, we do sometimes capture the magnitude in the spring, tend to underestimate that magnitude during the monsoon season. And one thing that is sort of curious, thinking about the carbon picture and the sort of potential insensitivity of the models to vegetation growth, to increases in plant water availability, is that the observed or the data-driven TET ratios start increasing slightly earlier than the model, and the model is a bit slower in many of these sites to increase that ratio, which could be because the model phenology isn't responding fast enough, but there's other things as well, like sort of gaining enough access to or root water uptake could be an issue as well. So these are all things that we really need to dive into more in the model. We just sort of documented them in this paper, and this is something that we're exploring now. So one thing that we're doing is, this is Kashif Mahmood, my postdoc, who I believe is participating here today. And he has been working on model optimization, so parameter optimization with the Orchidea model. He has a paper that's just come out in JGRB, and that was focused on optimizing the carbon cycle parameters, going back to that carbon piece, that looking at interannual variability in the net CO2 exchange. And he found that optimizing all these different carbon cycle related parameters for phenology and photosynthesis and general carbon allocation and turnover, etc., did improve that picture of the lack of NEE interannual variability, which was great news. We're just getting to exploring the impact of that optimization on the evapotranspiration, and he's also performing a whole bunch of optimization experiments trying to optimize more than just the carbon cycle parameters, all the parameters related to stomatal conductance and routing profiles, things like that, with a whole bunch of different data. So looking at GPP versus evapotranspiration and soil moisture data included in that parameter optimization. And he'll be presenting that at an AGU talk on the Tuesday, the 14th of December. So I really encourage you to look at that. But one thing just to highlight from the JGRB paper here, this is the same grassland site that I just showed you had that sort of delayed increase in vegetation growth, or potentially a delayed increase in vegetation growth. It's a sort of a guess or a hypothesis. And we can see this is the observations in black here. Sorry, the zoom thing is right in front of my plot. The prior model is in red here. This is for GPP, just to highlight GPP, not ET. And then the posterior model after the parameter optimization is shown in blue. And we can see a sort of, it's not offset here as it was in the TET ratios, but there is a sort of slower increase in that GPP that could be something related to a slower phenology scheme that was corrected by that parameter optimization. And one thing he did show was that the phenology parameters were really important for improving the sort of phasing of the carbon cycling in the model. So we're hoping that constraining the phenology parameters will help also with these sort of TET partitioning potentially, but that is something we're exploring right now. Beyond parameter optimization, though, parameter optimization can give you a sense potentially of where to look in your model to make improvements, because obviously things like GPP and ET are very coupled processes interacting with a lot of sort of sub-processes, and trying to figure out what is going wrong in the model is tricky. So we have a few other sort of pet hypotheses or theories, if you like, as to why things might not be working super well for evapotranspiration various parts of the year. Sorry. As I mentioned, for the higher elevation sites, really want to at some point dig into looking at snow cover and amount and duration, potentially partnering with folks at the University of Arizona and Joel Biederman, who have been developing this SnowView product. So that would be really exciting, but that is just, you know, a thought we've had. We haven't explored that any more than saying that. Another thing that I'm really interested in is more related to semi-arid grassland phenology. The way that the grass phenology typically works in these models is a kind of more like a temperate perennial grassland. So it kind of peters along throughout the year and maybe dips when it's cooler temperatures. Whereas we know that in these ecosystems, we've got maybe a mix of C4 winter grasses, C4 summer grasses, a mix of annuals versus perennials, and just capturing that diversity and that interplay, the sort of asynchrony of those phenological strategies might help us then have more of a response in the monsoon season at these lower elevation sites. Although I should add that I don't think that's the whole answer at all. I think we need to think about a lot of different processes that are impacting the ET and the carbon cycling. And but the other one that is sort of on the to-do list soon, if you like, is to test the new mechanistic plant hydraulic scheme in the model. So previously, and in all the simulations I've shown today, the water stress scheme is just an empirical function that has been shown in previous studies to not capture water stress very well. As you saw, actually, it was doing fairly well at these sites in that hot sort of May-June period, but we'd still like to test this scheme and see how it affects the evapotranspiration, as well as testing a more sort of dynamic root water uptake structure in the model. At the moment, the root water uptake is very static. We have no root growth as the soil profile dries, etc. So with that, I will just finish just to say that we're sort of very excited about continuing to test the model at these semi-arid sites, both very much coupled vegetation, carbon, water cycle processes. We need to sort of think about it all, obviously, to fully work out why the model might not be capturing some of the dynamics that we want to see. And so either in questions today or also in the breakout groups, if anyone has any thoughts on that, on any of the sort of model data discrepancies you've seen, I'd be really happy to hear your thoughts and suggestions. So thank you very much.
Thank you, Natasha. That was fantastic. And we have plenty of time for questions. So you have, I guess if you stop sharing, you'll be able to see that you have quite a few questions in the chat. So you can go through those. We also encourage people, if you would like to ask a question, use the raise your hand feature in Zoom. So if you click on reactions at the bottom, then there's a raise hand function. So you can do that, and then we can call on you and you can unmute yourself. So we have about 6 minutes here. Okay.
Great, I will go through. So the first one, what is the special thing for ET carbon coupling for the arid crops compared to forests or other types of canopy? I'm not fully sure about crops. If you're specifically talking about crops rather than the grasslands, I imagine it's, fairly similar picture. I don't want to sort of continue on something that I don't know very much about, but yeah, in terms of the non-crop regions, the grasslands and the shrublands, and Joel Biederman, Russ Scott, their synthesis really showed that this plant, ET is a sort of proxy of plant water availability, because of course there's lots of different processes that are going into that plant water availability, and it's really a measure of what water the plants are using, and that was really very strongly correlated with the interannual carbon cycle dynamics. It's Trendy. Sorry, I didn't explain that. Trendy is an ensemble of terrestrial biosphere models. It is a model intercomparison project that is actually performed each year across many of these global scale terrestrial biosphere models, and it's used actually in the global carbon budget. If you ever see that paper that comes out every year. What is this spatial resolution? Yeah. So all the ET, I should have mentioned this, sorry, all the water stores and fluxes simulations that I showed in this talk, it's all performed at site level. So we take the Ameriflux forcing data to run the model, the temperature, rainfall, relative humidity, incoming radiation, etc. And so we're not expecting a mismatch in scales because of a sort of more coarser forcing resolution at this point. It might be that still we're missing things when we specify the site characteristics. For example, another of my sort of pet theories is that often when we measure vegetation cover fractions, we don't necessarily do it at the time when it's peak productivity, and especially when we're using satellite data to estimate vegetation fractional cover, it's more of a kind of spatiotemporal average. Whereas in the models, when we're prescribing the vegetation fractional cover of each of these different vegetation types, we really want to set the sort of maximum possible vegetation cover, because the model processes themselves will limit that vegetation growth. And so some of the estimates of fractional cover at these sites have a high percentage of bare soil. And that means that the model will never, ever grow any vegetation in that bare soil fraction, which may not be the case, in a really good sort of wet year in the lower elevation sites, we might see almost, close to 100% fractional cover of the grasses. So, but we're not, so there could be things like that are not necessarily a mismatch in spatial scales, but still not prescribing everything we need to be prescribing accurately at the site level. And that's part of what the parameter optimization can help with.
Natasha, can I jump in? So we have 3 minutes left for questions, and Hugo has a hand up. So
okay. Yeah,
chance to ask.
Hi, Natasha. Nice talk. I really enjoyed it. So I was wondering if you have considered the cyclical nature of this of the seasonality in these environments, because in many places, especially in semi-arid locations, there's a legacy effect.
Yeah.
In moisture and also in productivity. So if there's, for example, a very wet year, the productivity will increase a lot. And the next year there will be more plants more able to use water, and and vice versa. So I was wondering if there's a way that you can incorporate that.
Yeah, and it's definitely something I'm trying to dig into, evaluating in the model, and also understanding that just from the data and from existing literature as well, and then trying to figure out, if there is legacy effects. When we're thinking about how to improve the model, it's sort of like, where does it come from, in terms of a process? Because, for example, snow melts building up over the winter, snowpack building up over the winter and then melting in the spring, that produces a bit of a legacy effect, or at least a lag, delay. But there are other many more physiological or ecological processes that might be contributing to legacy effects, and just unpacking exactly what they are, and then then we can dig into that process in the model to really see whether, we're not storing carbon enough in a certain pool, etc. We just, it's a bit of a tricky thing to dig into all the processes, if that makes sense. So yeah, but definitely wanting to sort of try and unpack that for these ecosystems. Yeah.
Thank you.
All right, thank you. So Natasha, we are just about out of time here, and so I want to keep us on schedule. You do have more questions in the chat, so please feel free to answer them there. We also have Slack channels. But yeah, thank you so much. That was wonderful. We'll move on to our next speaker now. Yes, so next we have, is it Simone or Simone? Can you?
Simone, yes.
Simone, okay, Simone, next we have Simone, sorry about that. Coming to us from the National University of Singapore, where I believe it is the middle of the night. Thank you so much for being here. And he'll be talking about physical and biophysical constraints to changes in evapotranspiration.
So, okay, thank you very much for the kind introduction. And first of all, I would like to acknowledge the organizer for inviting me here today. It's a pleasure to speak. And yes, good morning in California, but it's the middle of the night here in Singapore. And so I'm going to talk about changes in evapotranspiration and physical and biophysical constraint. So the research question motivating this presentation are actually questions which we probably share, many of us, which is how much has evapotranspiration changed in the last few decades, which are the drivers, and how will evapotranspiration change in the next decades. So I was asked to give this presentation on changes in evapotranspiration, and I realized that despite the fact I work quite a bit on evapotranspiration modeling and quite a lot on environmental change, I never really work on trends in evapotranspiration. So what I'm going to present is mostly based, it's a sort of a review talk based on mostly work of other people. So when we look at evapotranspiration, we all know that if we look at the atmospheric demand point of view, we have a few meteorological variables which are controlling evapotranspiration: temperature, radiation, wind speed, some metric of humidity, like VPD, which is also depending on temperature. And those are quite well summarized on the Penman-Monti equation, at least for the atmospheric demand side. So if you can think about one well-established equation, we can start to look potentially to trends in evapotranspiration. But of course, things are more complex than this, because atmospheric CO2 concentration is affecting the canopy resistance here through stomatal resistance. Water availability is not really included directly on the Penman-Monti equation, so you need to be parameterized in some other way if you want to use. And mostly, the role of vegetation is going to change several factors. It may change albedo, so net radiation. It doesn't affect directly aerodynamic resistance through roughness. It can change canopy resistance through leaf index and stomatal conductance. So all these effects may be embedded there, but even in that case, Penman-Monti equation depends on which formulation and you are using it, but it's also linearizing for surface temperature. So it's not really capturing all the feedback of surface temperature on change or net radiation, or sensible it as a proper solution of the energy budget should do. So using this equation, it can be done, but we should look with a bit of caveats. And if you're not even using a Penman-Monti equation, but something simpler, and I like this paper that was published a few years ago in Nature by Justin Sheffield and co-author, where after some discussion in the literature about trend in drought at the global scale, they were showing that if you replace a very simple empirical equation of evapotranspiration or potential evapotranspiration like turn weight that just depend on temperature with Penman-Monti, well, you pass from concluding that droughts, this is the Palm drought severity index, are changing, so increasing significantly to almost no trend, and also the area exposed to drought will not change that dramatic, has not been changing so dramatically as other previous studies were suggesting. And another study, which I think it's always important to remember, Mike Roderick was reminding us a few years ago that trends in potential evapotranspiration may have little to do with trends in actual evapotranspiration. He was taking CMIP-5 climate models to show that if you computed by the end of the century a few metrics like potential evapotranspiration or precipitation in comparison to the end of the 20th century, if you compare these two periods, the potential evapotranspiration change over terrestrial land surface it's 230 millimeters. But when you look at changes in net radiation expressed in millimeters, it's just 39. Precipitation is very similar. And this change in precipitation is roughly partitioned equally between an increase on evaporation, on evapotranspiration, and runoff or discharge. But the factor of difference is a factor of 10 between the potential evapotranspiration you will be computing with the meteorological variable and what climate model, land surface model were kind of predicting. So I was trying to collect a lot of references with regards to changes in the driver of ET, but I don't have time to present, otherwise the presentation would be too long. So I'm trying to summarize with the conceptual scheme, but believe me, all this is backed up with a literature study that I can show later on if you want. So if we look at precipitation, at least at the global scale, trends are not significant, also because precipitation interannual variability is very, very large. That is very difficult to find a statistically significant trend. But if we look at consideration based on Clausius-Clapeyron relation and thermodynamic and energy constraint, we expect precipitation to change roughly 2–3% per 1 degree of increase in temperature. So we should expect a slightly increase in precipitation. When it comes to air temperature and VPD, we all know very well they have been increasing throughout the last few decades, and all these should have led to an increase of potentially on ET. But then when we look at the solar radiation, well, there's been a decreasing from the 60s to the 80s, at least in North Hemisphere, in US, Europe. In China, this decrease was going on until 2000, roughly, related to what is called the global dimming. Then there's been a recovery from this global dimming in a global brightening, and most of these changes were associated to changes in aerosol composition. And more recently, literature suggests a kind of a tapering of solar radiation. When it comes to wind speed, there's been quite a debate about the global stilling that was going on from the 80s to early 2000, and also in this case, more recent literature show the wind is recovering, wind speed is recovering. When it comes to greening, there's been quite a bit of literature about trend in greening at the global scale, especially from the 80s to early 2000 or late 90s, and a reverse, which is still debated about more recent browning from the previous greening. And then finally, stomatal conductance should decrease because CO2 was definitely increasing on overall this period in a significant way. So of course, all these factors cannot be summed up, they don't have the same weight, the same role on ET. But if you want to summarize in a simple way, one hypothesis expectation was that from the 60s to the 80s, there should be some slight increase in ET, definitely much larger increase because of both temperature, radiation, and greening, they were all contributing from the 80s to 2000. And then maybe this is the decrease, this positive trend is decreasing more recently because solar radiation and greening, they are not contributing anymore, even though wind speed is recovering. So what studies are telling? If we look regionally, there was this study that caught my attention quite a lot from Rigden and Salvucci a few years ago, where we're showing for the continental US negative trend on evapotranspiration. So they were using a method based on analyzing in a specific way near surface meteorology, and they were finding a very strong negative trend over this period, which I have to admit is very unlikely realistic because this will imply a change of roughly 150 millimeters over 2 decades, which is the very large changes, should have been detected on stream flow and runoff, which is not the case. And indeed, this study was a bit different from many others that are showing a positive trend on ET. This is in China, mostly driven by changes in precipitation and temperature, with a trend of roughly 1.0 millimeter per year. Then there was this study in Austria, which I really like because it's one of the few based on the water budget equation. So trying to infer ET from precipitation and discharge in catchment in Austria, and was showing a very strong increase from 80s, 90s, and then a plateau on the more recent decade, with a trend which is very significant of 2.9 millimeters per year, and Austria is mostly energy limited system. Or another study in the UK with a longer period based on actually land surface model joules was showing a positive trend, mostly dictated by a change in precipitation and temperature, with the UK becoming wetter and warmer. When we move then to the global scale, I think probably there were some studies before, but at least for me, the study of Jung and co-author from Max Planck was quite important. And they were showing that a positive trend on evapotranspiration from 80 to 90s was actually reversed when we look from 1908 to 2008. And they were concluding that this negative trend was induced by a decrease in soil moisture. So we need to be careful because, of course, less soil moisture leads to less ET. But if precipitation doesn't change much, there should have been more ET in first place to lead to lower soil moisture. And indeed, it turned out that this study was very strongly affected by a transition between La Niña and El Niño event, as Diego Miralles was showing a few years later. They were trying to recompute the trend for a longer period and showing that there was no significant trend at the global scale, but definitely the evapotranspiration anomaly on the south hemisphere and tropical area are strongly related to dynamics of La Niña and El Niño, especially when you have a La Niña event, you tend to have a peak of positive evapotranspiration, which is then probably removing enough soil moisture to start creating a negative anomaly of ET, combined also to less precipitation during El Niño event. So if you start computing your trend analysis exactly on those periods, and there were at least 3 on the last few decades, then you will get a negative trend. But if you look throughout, the trend was not significant. And if you take almost the same period, but you indeed exclude this 80-82 period with La Niña and El Niño, as this study of Zhang and al., then the trend became significant. You see, not significant 80 2011, significant 82 2011, and with recovering also this negative one from 1908 to 2008, with a magnitude of roughly 0.76 millimeters per year. And a more recent comprehensive study combining different remote sensing product with different land surface model and machine learning approach, they were also recovering an overall positive trend in the same period, with a larger magnitude on remote sensing product of roughly 0.6 millimeters per year versus 0.23 from land surface model and 0.38 from machine learning, with relatively similar spatial pattern, with a decrease in Southwest US, while an increase in evapotranspiration mostly on Kalahari, Sahel, India, China, and North latitude, including Europe and some part of North America, North latitude, especially where you have forest. And the fact that the land surface model were producing a lower trend was associated to the fact that remote sensing product may tend to underestimate the effect of CO2 enclosing the stomata. A study published a few weeks ago actually is recovering a quite similar trend of 0.8 millimeters per year. Again, relatively similar spatial pattern. Is not surprising because many of these studies, they're based either on the very same product or at least on the same combination of remote sensing product and reanalysis climate data. So there is a correlation between all of those. And they were attributing this trend in this study. They were using land surface model to do a partition of the causes. And they were saying, well, most of the trend is related to climate effect because CO2, if anything, has led to a decrease in evapotranspiration because stomatal conductance decrease is more important than increase in Leffler index. And land cover change, there were not very significant effect at the global scale. So Some plays were induced by changing precipitation, but I think personally there is a very strong effect, which here is embedded in climate, of the greening occurring in the north latitude on the extension of the growing season more than in the increase in the leaf area index. So I think part of this positive trend, which is recurring in many of these observational data sets, is related to the extended growing season in north latitudes. But one thing we should remember that if you take the ensemble of models here versus the GLIM that they were using as a remote sensing product, the trend, well, there are some spatial patterns which are similar, but the magnitude was quite different. And I actually discovered recently one paper from Zhang et al., which was published in 2012, where they look at the water budget trend in evapotranspiration from water budget in roughly 200 unregulated catchment worldwide. And they were comparing this trend with trend estimated from the machine learning approach of the Max Planck Institute and the Penman-Monti-Loening approach. And while in dry catchment, there is some correlation, or roughly half of the variability is explained between these two different products. For wet catchment, there was no whatsoever correlation between the two products. And I think this is partially related to the fact that sometimes this machine learning extrapolation or some remote sensing driven approaches, they tend to not consider properly some of the water budget and energy budget constraints, which are extremely important. Let me show a few examples of this. First one is coming from University of Michigan Biological Station, where they ran an accelerated manipulation experiment where they girdled aspen and birch, reducing of roughly 40% of the basal area in the forest, so they accelerate succession, killing trees. It took a while for the trees to die, but after roughly 3 years, they reduced indeed the basal area and also the leaf area index of almost 50% in the forest. But despite this huge change that you think in the leaf area index, well, flux tower observation were suggesting that the gross primary production was not that different. I'm not entering the detail of why here. And most important for this discussion, latent heat was pretty much unchanged despite a strong change in vegetation. And I think this is related to the fact that the energy and water that they are going into the system are pretty much the same. And the forest is kind of responding to this. Another, I think, striking example, this one from my work together with Jason Beringer at the University of Western Australia. This is a case of a wildfire, a bushfire in Australia, which occurred in early 2009. And these are simulated with the terrestrial biosphere model, latent heat and gross primary production. And immediately after the fire, which damaged 100% of the canopy, you see 2-3 years later, the model suggests that evapotranspiration is almost completely recovered to pre-fire level, despite the two ecosystems, they look very different. One is a eucalyptus forest, 100 years old, 80 meters tall, and the other one is a few meters regenerating forest. And this, you may say, okay, this is a modeling result, but this is a lucky case where there was a flux tower, which was recording before the fire. It was restored a few months after the fire. And you see the flux tower, if anything, suggests even a faster recovery than the model. So as soon as the leaf area index rebounds to some decent level of the pre-fire condition, the system is again transpiring at evapotranspiring at pre-fire level, both in the model and in the observation. And I think, again, these energy and water constraints are extremely important. And to show another example of this is a study that we ran a few years ago where we were looking at the effect of elevated CO2 passing from 375 ppm to 550 ppm on how it was changing. Actually, we were interested in net primary production and especially in partitioning direct and indirect effect. So these are 44 sites, mostly corresponding to flux towers, and wetness index is just from arid site to wet site. It's a precipitation divided potential evapotranspiration. So if you look at this site, changes in ET because of this change in CO2 were on order maximum 6-8% on some of the wet site, and they were then going down to basically zero in arid site, which should not be surprising at all, because any time you go to arid site, ET changes are related to precipitation changes. So if precipitation doesn't change, it doesn't matter how much CO2 you have or what's your dynamic of the leaf index. And indeed, if you look to the partition between the direct effect through stomatal closure here will be of a reduction of evapotranspiration, even more significant in dry site, around 15 to even 10-15%. But this is counteracted by all the indirect effect related to increase in leaf area index or water saving of soil moisture, which are then basically contributing in the opposite direction. All this indirect effect. And before arriving to the conclusion, let me show this example, which I think it's important. These are unpublished results, but it's one, I think, of the few cases where we have in the same place a flux tower, a lysimeter, and then we run the terrestrial biosphere model TNC. This is a Rittelsbach in Switzerland. And if I don't put the label in this plot, it will be very hard to say which are the two data and which is the model. So if now I put the labels, this is a lysimeter versus simulation, flux tower versus model simulation, and flux tower versus lysimeter. So if you only have the flux tower, you will likely conclude that your model is explaining 80% of the variability. But now that you have two types of measurement, my conclusion will be that these are three equivalent representation of reality, which pretty much the same level of uncertainty. And indeed, a very nice paper in Science several years ago was reminding us that when it's about the open natural system in earth science, verification and validation are pretty much impossible. At the best we can aim, it's about model confirmation. So coming to the conclusion, again, this is mostly not based on my work, but I think one important message is that any methods which is not properly accounted for energy water constraints, so it doesn't solve for surface temperature or soil moisture, and it doesn't account for CO2 effect on vegetation, which is the case for many remote sensing driven or machine learning driven approaches, may embed some deficiency, especially when you look to trend in evapotranspiration. It may be good to look to spatial patterns, but trend is a different story. I think that land cover changes effect on ET in absence of significant change in water supply and net radiation may be often quite limited. So even though the ecosystem may look like very different, but the overall, if the energy and water that goes into the system and it's related to the old Boudico framework are the same, the change in ET may not be expected to be very large. And the role of elevated CO2, which is something I studied myself more, on changing ET has two contrasting effects. As we know, is it may increase leaf area index and reduce stomatal conductance, but because those two are contrasting effects, the overall net effect may be relatively small, despite considerable changes in gross primary production and water use efficiency, which has been observed and we also simulate with the model. And with this, I thanks for your attention. I'm ready to glad to take questions and to participate to the discussion later on.
All right, Simone, thank you so much. That was a fantastic dive into the literature. I really appreciate that. So we are at 9:20, but I do want to allow for questions. So let's push back 5 minutes. We'll start break in 5 minutes and allow some time here for questions. So please use the raise your hand function if you'd like to ask something. You can also type questions into the chat, but please feel free to raise your hand and use your voice. Shulang has a question. Go for it.
Yes, my question is, what's your suggestions on the quantitatively analysis of the ET, global ET trends? I mean, can we attribute the ET trends to how much of the ET trends can be attributed to the air temperature, or how much can it be caused by the canopy like NDVI or soil moisture? Can we do that?
Some of those studies, I think one of those I showed, the one published in 2021 in Agriculture Forest Meteorology, is exactly trying to do that using, well, you need to use model to try to partition this effect, or some fancy statistical analysis or remote sensing data, or maybe both. But there are divergences between different papers on the importance of the role of vegetation versus climate. Mostly, if I have based on my, again, it's not my own work, it's more my assessment of the literature. I think that this positive trend, which I think it's true because there are so many different line of evidence going into that direction, especially from the 80s to 2000. Maybe it's not as strong anymore in the most recent year. I think it's related to the extended growing season on North latitude. I think they have contributed quite a bit. And they also, I think the increase on VPD may have contributed more toward the temperature to an increase on evapotranspiration in energy limited region than anything else. So I think it's the combination of these two aspects. While CO2, I base also on my own result, I think if anything, has contributed negatively to ET, but probably on a very small, it's a very small effect. And I think effect of wind and solar radiation are probably also a little bit smaller, with a few exceptional solar radiation in certain regions where trends have been very significant on the brightening. There are some places in Switzerland where shortwave radiation has been increasing 30% on the last 30 years, which is crazy. But even there, according to our study, mostly it went to long wave reflected radiation. But so I think there is still more to research, but that's overall my impression if I have to summarize.
All right, thank you. Diego, would you like to ask your question?
Hi, yes, I do. Thank you for the presentation, Simone. It was really interesting, actually. I was just missing one paper that came this year, actually, in 2021, with this increase in 10% in global land evaporation from the group of, well, it was actually from Madeleine Pascolini-Campbell in Nature. And that kind of like confirms what you just said, that probably the CO2 effect doesn't really matter so much. So I was just going to come back to this statement about remote sensing trends, right? Which is true, and I think it's true for the majority of remote sensing data sets. Not all of them. Some of them have encoded the fertilization effect the same way that land surface model would, right? But in this case, actually, in this Nature paper, based on GRACE, which was in principle independent from this parameterizations, there was still that 10% increase that has been reported by remote sensing data sets in the past. So what is your view on that? And actually, if I were to just ask you out of the blue, like, do you think evaporation is increasing based on this meta-analysis? What would be your point of view?
Well, I think so. I mean, I know I didn't have time to include all the papers in the presentation. Otherwise, it would have been much longer. And I had to review actually a lot of this trend on the driving variables, which was. But I think, I mean, I agree. I think many different pieces of evidence they are bringing to this increase in evapotranspiration. So I think this is occurring. If you have to give a magnitude, I think it's probably more on this. It's probably slightly less than some of the remote sensing products are giving, probably a little bit more than land surface model. So on this 0.5 millimeters per year, probably it's a good order of magnitude, which also will correspond to what you will expect in the long term as an increase of precipitation based on the change of temperature we had in the past. So I think there is a coherent story, and if I have to think to the major driver, I think it's really probably has been related to this greening on north latitudes and some release of energy limitation in certain places, which could be again north latitude, but also tropics, because there are certain parts of the tropics. I think that's what my impression is going on, and I agree with you. Some remote sensing products are now including effects of CO2 or more detailed analysis and I think we will converge there to have all this proper constraint of water and energy budget into hybrid products, which are not purely remote sensing and not purely modeling either. I think you are probably already quite far on that yourself, so you may know better than me.
All right, thank you. I hate to cut this off, but I do want to try to keep us relatively on time. So let's, Guy, would you mind putting your question in the chat? And Simone, you have other questions there, and please feel free to keep adding them, or you can move over to the Slack channel. We are going to go on break now. We will take a 10-minute break. So we will reconvene, let's say at 9:40.